Deep Learning with Pytorch, Lesson 6. Today we are going to be going over Chapter 4 in the book. I don't think we're going to make it all the way through Chapter 4. Chapter 4 is Real-World Data Representation Using Tensors. We'll go all the way until we get to the text. It'll be very close to the end of the chapter. If you look in the file where all of the code is, and we go to this one, chapter 4, we're going to cover the first 4 of these here. So let's get right into it. A lot of these aren't too complicated, so it shouldn't be that much. And yeah, here we go. So when storing an image as a tensor, and we've talked about this already, what we have here are length and width, and then 3 channels, RGB. If it's a grayscale image, there'll only be 1 channel, but in this case, the value of red, green, and blue. So when you see these high intensities, that's because that is red on the spectrum, so it's high intensity, it's white. The clouds are white in all of them. Green has a high intensity for the green stripe, and blue has a high intensity for both the blue stripe and a pretty high intensity for the sky as well. So you can just kind of think of it as three matrices there. Alright, so now we'll just jump right into the code since it's not too hard. Let me go ahead and restart and clear all my output here. I've looked at all of these codes already, and it's not too. They're not too complicated. I have played around with them a little bit though. So edge items, what this means, I'll explain it as we see it. But we're importing as numpy as np. We're importing torch, and this is print option. So it's just when we print out a tensor, there'll be 2 items on the edge and a total threshold of 50. So what is the shape of the image Bobby? So we can look up where the image Bobby is. I think we did use it in a previous lecture, but if we go to the main file, we go to data, we go to chapter 4 data, there's an image, I think an image dogs of Bobby right there. So we're just loading that image and saying what's the shape of that. Okay, well the shape is 720 pixels by 1280 pixels by 3 color channels. So now we're going to rearrange that. We're going to do a permute on it, and let's see what that looks like. So image torch from numpy. Why are we getting the same shape? Oh, okay. This is just the same shape as above. So we're saying this image is equal to torch from numpy image R, and image ARR is Bobby, and then out is we do image permute this. So if we said out.shape, we would get a different shape. So what do we do here? We put the 0 here. We put the second one in the front. So it goes 0, 1, 2. So this is 2. 2 goes to the front. This is 0. 0 goes to the middle. And 1 goes to the end. So we're basically just moving the 720 and the 1280 back and putting the 3 in the front. And that's the general way we want these to be organized. We're just kind of mixing our dimensions. So when we feed them in, that's into a neural network, this is normally the standard format. Okay, that's what I'm looking for. Standard format that you want for the images to go in. Now remember batch size. Batch size is a group of images. So we'll run that, and we'll run that. And the RGB color scale goes from 0 to 255. So what this does is it normalizes that. It's just normalizing that. And here's another way to normalize the color channels. So I think that there's a part in the book that describes this. Yeah, so one possibility to normalize it is just divide the pixels by 255, which is the maximum. So any number up to 255 divided by 255, that will give us a value within 0 to 1. So that normalizes it between 1 and 0. This is another way to do it where we take the mean of it and then the standard deviation and mean divided by standard deviation. So if we look at normalization equations, like just Google normalization equations, we'll see quite a few. The log scaling. The one that we'll see quite frequently used in this line of work is the z-score. The value minus the average divided by the standard deviation. And you'll also see it if it's on a scale, then you can just divide by the max of that scale. So like I said, any value divided by 255, 144 divided by 255, that's going to be 0.5. So all the values in there from 0 to 255 will give us a value within that range. I think that just about covers everything. Let's look at the batch shape to get an idea of that. So our batch is actually a 4-dimensional tensor. So we have, this is our images, 3 color channels, 256 by 256 pixel. And what does this 3 stand for? Well, that's the 3 different images. So if we kind of look into this code here, we're saying batch size equals 3. Okay. Batch equals torch.zeros, 3, because batch size equals 3, by 3, by 256, by 256, and we want our units to be integers of 8. Okay, so that's a 3 by 3 by 256 by 256. And at this point in the code, it's going to be all zeros. Now we're going to fill these tensors with data. And we're getting that data from this folder here. So we can track that folder down pretty easily. We go to data, chapter 4, cats. Okay, so there's our 3 cats. This is going to be our batch size, the pictures of these 3 cats. Now we're saying to read that file, input it as a tensor, organize that tensor. Remember, we put it in the color channels first, length and width. All right, and this is just saying, I guess, do it for all 3. And then batch I will equal image T. So then we normalize our batch. So we're normalizing our batch via this method, but we could have done it this way too. So we do it this way, and then we redo it this way. So you could delete either one of these lines of code, and your batch would still be normalized. So now let's look at the shape of the batch, like we just did. And now I'm going to show you that this is code that I added. Just kind of playing around with it. I want to take the first image, okay, which would be batch. We index the first one, and then we say all, and all. Okay, and what's the shape of that? Okay, it's 3 by 256 by 256. All right, so now we need to permute that. I don't know why we would need to permute that. Yeah, that will not work. And another thing I need to do is import matplotlib as PLT. mshow. What is the import for this? Import mshow. So maybe this was the line of code that I needed here. Okay, and there we go. It worked. So we needed this code here. I was just playing around with this, and I guess I messed it up. So it says clipping input data to valid range for mshow with RGB data 0 to 1 for floats or 255 for integers. So what we just did here was we re-grabbed the image out of the batch. So we took an image and turned it into a tensor, and now we're just taking that tensor and turning it back into an image. So we're grabbing the first one of the batch. We're permuting it into the right. We're reversing the permutation. That's what I was doing here. Okay. Reversing the permutation because it has to be in this format in order to plot it using this plt.mshow. So if I take m1, it will not. It'll tell us, hey, this is an invalid shape for image data. We want it to be 256 by 256 by 3. So that's why we do that. So something we'll learn later on with GANs is that initially GANs start out with random data. So let's create another image, and we're just going to do a random numbers of 256 by 256 by 3. So let's see what this gets us. This will be kind of interesting. Noise. Just noise, right? Just a random plot of red, green, and blue. So we could set, you know, a whole square of this to be red if we wanted to, if we just zeroed out all of the blue and the green values and said make all the reds max, and we can make a red square, we can make a green square, a blue square, and we can put this into different neural networks and get different things. So this is just an idea to show you that this is how the data works. That's all your computer sees is a tensor when it's plotting these images. So now we'll go to the next one. This one's very fast. It's really cool though too. So let me kernel, restart, and clear output. Okay. So again, here's the edge items. Let's go ahead and run that. Now we're grabbing the lung data from our standard folder. It takes a minute to load there. We ask what the shape of that is. It looks like the shape of this one is 99 by 512 by 512. Okay. So now we have one. We unsqueezed it one dimension here. And now we have that. 1 by 99 by 512 by 512. And if we plot it, we get an image of the lungs. It looks like we have 99 different layers. So this looks like probably the midpoint, because that runs from 0 to 98 in here if we want to look at them. So if we look at 20, we should see it maybe a smaller cross-sectional area of the lungs. Yep. And if we go to 10, maybe even smaller. Yeah. And maybe if we go to 0, we won't see it at all. We'll just be at the bottom of the lungs. I hope these are lungs, by the way. It says lung. Okay. If we go to 75, I mean, they look like lungs. It looks like something's wrong with these lungs, huh? So 50, the midpoint, it looks like there's some type of thing going on here. And if we go to the top, 98, we should be at the top of the lungs. So this is just a standard CT scan where we are slicing through and looking at each slice of the lungs. I want to see what it looks like in this folder, just because I don't know what that data even looks like. Volumetric DICOM, lung. So it's just these DCM files, and there's 98 of them. So yeah, I guess maybe that's a CT scan type file, a DCM file. Okay, so that is that. I don't see an RGB color scale on this, because the 99 is indicative of the layer. Then you have 512 by 512. So I'm not sure where the RGB falls into that, but basically they're just showing us that we can slice through it, and this is just another way to store data. This is in a 4-dimensional tensor now. Okay, so now we'll go to the next slide here. And this is tabular wine data. And what we have here is we will import our necessary modules again. And now we're going to import this CSV folder from this path. And we're going to be using a little bit of machine learning on this code, but we're not going to really crack into the neural networks. It's more just about data analysis from this path. So let's import this data, this CSV folder. If we look at this, it says NP load text. That's wine path. Data type is float32. And the delimiter is a semicolon. So that is what separates the columns within this data set. So we'll run that, and then we have a tensor. And if we look at our Excel spreadsheet that we just imported, this is what it looks like. So it's not a very normal looking Excel spreadsheet. If you make any changes to it, it'll mess it up. Each of these cells have these semicolons in between the data. And so we told our Python code to separate these based on these semicolons. All right, so next we have the column list here. Next, CSV reader, and okay, let's see what that looks like. This is pulling up the very top of the Excel spreadsheet and telling us what they are. So we have different categories within this data set. It's a wine list. So fixed acidity, volatile acidity, citric acid, residual sugar, all the way down to alcohol, quality, all of the important data points. So quality is, I guess, what we would want to predict, and that is in the book here. Here's the CT scan. And here is all of the data within the Excel spreadsheet. And what we're going to try to do is see if the quantity of sulfur has any prediction on the quality. So that's just a basic linear regression problem. Let's keep moving through this code, and I'll keep explaining it as we go. So now we're going to get another tensor here. And basically what we're saying here is we're asking what is the shape of this tensor and what is the data type. So it is 4,898 units long and 12 categories at the top, 12 columns. So these are the 12 different categories, and if we kept scrolling down, we would eventually see that we have classified 4,898 different types of wine here. So now let's look at this one. So what is this line of code doing here? We are indexing a tensor, right? So we're saying all 12 columns here. We want or no, sorry, all rows. The first dimension is rows. The second dimension is columns. So we say, hey, we want every single row in the data set, but we don't want the last column. So this is all of the variables for our data set. So now we have subtracted one column off of our data set. And now we have the same amount of rows, but one less column. That column that we subtracted off was the final column, which is quality. Okay, so target looks like this. This one is saying up to the last column. This one is saying just the last column. That's all we want. So target is a common phrase used when you're dealing with machine learning or neural networks. Target is normally your target variable, what you want it to be labeled. So this is just a one-dimensional vector, 4,898 units long. Each of these is indicative of the quality of the wine. So we could find out the max of this. How to find max of a tensor Pytorch. You'd say torch.max. Okay. So let's do that real quick. We can press A while we've selected the box, and that will add, or let's press B, that will add a box below us. So torch.max of our tensor target. The max is 9. So what is the minimum score? And these are practices. You got to learn this stuff in order to get a good idea of your data set, so you can apply the correct machine learning algorithm to it. So now we have a wine equation here. So what do we do here? I think all we're doing here is changing the type of data. So if we said up here, it is a float 32. Okay, and now let's say comma target dot d type here. Now it is an int 64. So that's what this addition on here, dot long, and we learned that in the previous lecture, that may change the data type from float 32 to a 64-bit integer. So one hot. One hot is a way to. I think one hot is more clear on the next code, which is the time series stuff. I don't remember what the one hot was supposed to do in here. It looks like we're saying 0, 10. Let's just run this and see. Yeah, I think I'll explain one hot better in the next code. I don't remember looking at it in this. I don't even see any other use of it. But one hot is an important concept to get. You do have to use that a lot when dealing with categorical data. It is a way to systematically organize the categorical data in the form of a tensor. So target unsqueezed, we're going to unsqueeze our target by one dimension. So it was a one-dimensional vector. If we look at target dot shape, it will be that's target shape. If we look at the unsqueezed shape, it will be, I think it'll be 1, 4,898. Let's double check that. Let's try and spell correctly. That might help. So yeah, we added another dimension, one dimension there. So that's all the unsqueezed command does, is adds a dimension to it. Now let's calculate the mean. So now we're back into data normalization. Again, we did a simple Google search on that, normalization equations, and there's a bunch of different normalization equations. They're all pretty straightforward. Here's one that you see a lot, the minimum over the max minus the min. I'm sure that we'll see the one we're using somewhere in here. I mean, it's super common. I don't see it, but it's the average minus the variance. So right now we're calculating the average here, which is the mean. Okay. Now we're going to calculate the variance of that. And now we're going to normalize it. Our data minus the mean minus the square root. And now our data is normalized. Our whole tensor is normalized. If we look at the wine quality spreadsheet here, you can see that some of the values in this are like 170, 132. Now all of the values are between 0 and 1. And you can see that here. And also that brings me back up to the top here. When we said edge items 2, that's why we only see 2 values here. So if you want to see more because you're trying to figure out what's going on, you could write 4. And then when we rerun that code, I don't think I ran the top code. Okay, now when we rerun that code, we should see 4 on each side. Yep, so now we have 4 values here. We don't see any values above 1. So, okay, so our data is normalized. We're good to go. And just to reiterate, this is calculating the data mean. If we look at the shape of that, it's 11. That's indicating our 11 categories. Data was up here. Here's the 11 categories. All right, so that's the average of each of the 11 categories, the average score for each of these categories: fixed acidity, volatile acidity, citric acid, all of them. And this calculates the variance of each of those categories. And this normalizes the data. And I said it normalizes it between 0 and 1. That's not entirely accurate. It just normalizes it into a standard normal distribution. So it could be below 0 as it is here. It could be above 1. But it does follow a standard normal distribution. And that's a basic statistics thing that we're dealing with here. That's the Z equation that we learn in statistics. All right, so now we're going to grab the bad indexes, which is the target is less than or equal to 3. And we'll look at the shape, the data type, and the sum. So the data type is Boolean. A Boolean is a true or false value. The size is 4,898. The tensor is 20 length, a length of 20. So what are we saying here? Bad indexes. We're grabbing all of the bad wines, I guess, because it is less than or equal to 3. Oops. Control Z that. If you remember, I did say, what's the minimum for the target? It's 3. So 3 is the worst score it could get. I believe the score goes from 1 to 10, but they never gave out any 1s and they never gave out any 10s. The lowest score they give out is 3, and they gave it out 20 times. Okay? Yeah. So that's that. Now we can look at those 20 wines. Here they are. So we said bad data equals data with the bad indexes. what did our bad indexes look like? Let's just look at that. Bad indexes. False, 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 false. So it's just a tensor of 20 long. They're all false. They're all less than or equal to 3. Well, how does it grab this data from this? I guess it's indexing those tensors. Oh, because all of this comes from the same original governing tensor, which was our original data here. Wine equation here. This is what we gathered from there. So it's all coming from there. So it still knows to index it from that. So that's where it gets a little tricky. But yeah, this is our bad data. These are all wines that scored a score of 3. These are the values that they had, and all of this data has been normalized as well. So let's keep moving along here. Now we're going to do a few more things here. We're going to say bad data is here, mid data is from 3 to 7, and good data is above 7. Okay, so we run that. And what we're doing here is saying find the mean of each of the values and find the the mean of each of the values. That's all we're doing. So here is our bad data, here's our mid data, and here's our good data. So if we look at sulfur dioxide, we can see that the bad data has a high amount of sulfur, the mid data has medium sulfur, and the good data has a lower range of sulfur. So the prediction, I guess, that you make here is that sulfur is the best way to predict whether the wine is good or not. So we'll try that out. And here, I think I added this line of code just to see how many bad, how many mid, and how many good there were. And there was 20 bad, that many medium, and that many good wines. Total sulfur threshold. So this is something from the book that they chose to do. They said, let's take this, and if the sulfur is at this value or higher, we'll call it bad data, and if it's at this value or lower, we'll call it good wine. So let's do that. All right, and we get a value of 2,700. Let me just run these lines of code to figure out. It's kind of hard to remember all of these. Okay, so yeah, actual indexes. We're predicting whether the score is at or above. No, sorry, just above 5. Is the score of the wine above 5? The actual index is shape, is that many, Boolean, and the actual index is sum. So if the wine has a score higher than 5, we have that many wines that have a score higher than 5. That's 3,200 wines. Okay. Our predictor here predicted 2,700 wines, and this is based on the sulfur threshold. Okay, so how many of these are lining up though, right? Because this is, some of these wines here might not have a score higher than 5. So that's where we get these percentages here. So how many match? How many of the in this category match up with this category? Only 2018. Okay, so that's 75%. And that gives us a prediction rate of 60%. So if that shows that that's not a very good prediction rate. We could use a neural network on this data. It's not hard to do that. It would be much easier. This is obviously like nobody would say that this would be the best way, but it's just the book showing you like how to look at a data set real quick and start exploring with it. Because sometimes there might be a predictor that does work that well, and then you would want to go that way. So our prediction method of saying, hey, a score of 141, a sulfur dioxide content of 141 or lower is a good wine, and 141 or higher is a bad wine, you get a prediction rate of 60%. An accurate prediction rate of 60%. So now I wanted to plot that because in the book they had this plot, so I tried to recreate it. And that's this plot here. And I'll show you why that didn't work initially. So let's go here and run that. Well, I'll show you the good one first, since I guess I have to. Okay, so what I did here to plot it was I took the average of each value of the sulfur content. So right here, I'm gathering all of the data for a score of 3, a score of 4, score of 5, score of 6, 7, 8, 9. And then these values here, I'm saying, all right, take the average of the 6th column. And the 6th column was, in fact, the sulfur content. So now I'm taking the average of that. Now each of these is just the average sulfur content for that score of wine. And then I'm just creating a tensor here, which is 3 to 9. Did we get the shape here? No, we didn't, because I don't have that at the bottom. So if I put that at the bottom, we will see the shape. The shape is 7. And I'm turning this, all of these together in sulfur average, I'm turning that into a NumPy tensor in this line of code. So I have a length of 7 here. If I said comma wine score dot shape, this should also be 7. Oh, it's a list. It has no attribute of shape. Well, I guess it didn't matter because it's still plotted, so that's no big deal. So x equals wine score, y equals sulfur average tensor, and this is the plot that we get. Average sulfur content based on the wine score. We can see that the 3 has a very high, but then 4 drops, and then you can kind of say it predicts for these higher ranges, but this does not look like a very good predictor. Maybe if the 4 value is up here, but the sulfur content drops significantly to 4, and if your wine score has a score of 4 or 7, it basically those have the same average sulfur content. So that doesn't look like a good predictor. This is how I tried to plot it at first. Let's see if, yeah, it did plot this time. So by trying to recreate this plot, it just doesn't work because these are integer values from 3 to 9. You're not going to see these values in between. They can't get a score of 3.5 or 3.2. So this plot is not able to be recreated in this manner. And that's all that I'm showing here. Okay, so I think that's a good place to stop. I'm actually going to do this time series in the next lecture, and I will also do the time series, or the text. Let me find the exact words to call it. representing text using numbers and looking at data sets that are composed of text. I think Jane Austen is an author, so they're just breaking some of her text down into code. And these are just extra lessons here. Maybe I'll look at those later and get those up. Okay, thank you for watching this lecture, and I'll see you